Once again, good morning, students. I would invite Himanshu sir to start the session.
Good morning, students.
Good morning,
Is it
sir.
visible?
Yes, sir.
Yes,
Okay.
sir.
So, in the last class, we were discussing about VBT, VSEPR, and the last topic was hydrogen bonding. Okay. So, before that, just tell me, in the last class, I was asking about the boiling. What is boiling? I told you that just to learn. Remember?
Yes, sir.
So, can you tell me what is boiling?
The transition from liquid to gas or vapor,
So, that is
gas vapor.
evaporation or vaporization, I think.
No, sir. By heating, no, sir.
By heating, okay, it is converting into the gas in liquid from the liquid form to the gas form. But I'm
Yes.
taking out what exactly the boiling term represent. See, it is a sort of condition. Just because it is sort of general knowledge thing also. Yeah, what is boiling? Okay, so the condition is like whenever there is a solution and we are heating it at that particular time, the liquid start converting into the vapor phase, and at that particular time it will exert a pressure that is known as vapor pressure. It will exert a pressure on the surface of liquid that is called vapor pressure, and when this vapor pressure becomes equal to the atmospheric pressure, when the vapor pressure of the liquid become equal to the atmospheric pressure, that condition is known as boiling. Only at that particular temperature or at that particular when this two conditions become same, at that time the liquid start boiling. Otherwise there will be no boiling. The temperature of the liquid will rise up. It's obvious that the liquid temperature will rise up, but it will not become equal. There will be no bubbling, there will be no boiling, whatever you say. So just remember the condition at which the vapor pressure of the liquid becomes equal to the atmospheric pressure. That condition is called boiling. Okay. Hello. Next thing. So we were discussing about the hydrogen bonding. So in the last class, I told you that two type of bonding was there. Have you revised the last class?
Yes, sir.
So the two type of bonding was intermolecular and intramolecular hydrogen bonding. If it is happening between the same type of molecule within the same molecule, then it is known as
Intramolecular.
intramolecular. When it is happening between the different molecule, it is known as intermolecular. Okay.
Intermolecule.
Yes. So if I talk about the difference, okay, so different base difference, so that different in same molecule. But what exactly happened? What is it? What it impact? What is the impact of this particular thing? That is, there's a different thing that when two molecule will hold each other, two or three molecule hold each other by the hydrogen bonding, and one condition is like in which there is no within the same molecule and there is no other molecule is there. So in this type of bonding, if you'll see that in case of intermolecular hydrogen bonding, each molecule are holding each other, due to which if we want to break the bond, the more amount of energy is required. See, in this condition, if I want to break the bond, I want the solution to boil, the boiling and melting point of intermolecular hydrogen bonding will be more. The boiling point will be more. Why? Because more interaction is there. If more interaction is there, more amount of energy is required to break the bond. So if more amount of energy is required to break the bond, it means the boiling point of the solution will easily rise. But in this case, there is only a one molecule. So there is no interaction with the other molecules, so they will not hold each other. So just because it is in the same molecule, so there is no holding up of molecules, so it will easily boil. So the boiling point of intermolecular hydrogen bonding is more than the boiling point of intramolecular hydrogen bonding. Second thing, if I talk, first thing was boiling point and melting point. Same thing, intermolecular will have high, intramolecular will have low. Okay. Second thing, if I talk about volatility, what is volatile? What does the mean of, what does this word represent? Volatile. Anyone? Okay. Listen. If any of this substance, any of the liquid or solid, whatever it is, okay. Basically, we talk about liquid in case of volatility. Okay, when it start converting into the gaseous form or vapor form without heating at room temperature. At room temperature, if any of the compound is converting into the gaseous phase, that is known as what? Volatile compound. Okay, can you give me any example of volatile?
Evaporation.
Example. Evaporation is a different thing. I'm talking about the example, which start rapidly converting into the gaseous form.
Petrol.
Petrol, very good example. That have you, if you remember the Corona period, we were using sanitizer. Remember?
Yes,
So,
sir.
so while we were using sanitizer, it just fade away within the second. It was not completely going inside our skin. It was most of the compound were volatile. Okay, so the ethanol, volatile. And second thing, what we can say that petroleum products, they are volatile. Okay, so if I talk about the volatility of the compounds, volatility is inversely proportional to the hydrogen bonding. Volatility is inversely proportional to the hydrogen bonding. If it means, if if there is more hydrogen bonding, then the volatility will be less. So now tell me, in case of intermolecular and in case of intramolecular, which one will have high volatility? See, I told you more hydrogen bonding, more volatility. Now in this case and in this case, which of the compound is having more hydrogen bonding? HF or orthonitrophenol?
Intramolecular.
Intramolecular is more volatile. Why more volatile? Because in this case, there is bonding within the molecule. But if I talk about HF molecule, there is bonding within different molecules. So number of hydrogen bonding is more. So if hydrogen bonding is more, volatility will be less. Okay. So it will not be volatile. It will not easily vaporize, or it will not easily convert into the gaseous form. Okay. One more thing. Third, hydrogen bonding. Hydrogen bonding is directly proportional to the viscosity. See, molecule will not easily move if there will be more interaction between them. So if there will be more interaction between the molecule, if there is more interaction between the molecule, it means they will not easily move. The viscosity of that particular compound will be more. But if there is no interaction between the different species, or just talking about an intramolecular condition. In this particular condition, there is the viscosity of the compound is very low. Okay, so these are the three factors, but you have to remember the boiling and melting point. The boiling and melting point of this intermolecular will be more, intramolecular will be less. Okay. Second condition, volatility is inversely proportional to the hydrogen bonding. Third condition, hydrogen bonding is directly proportional to the viscosity. Okay, so clear this thing. Yes, any doubt?
Sir, can you explain
No, sir.
viscosity?
Viscosity is okay. I'm giving a basic example. Ketchup versus water. Ketchup versus water. Which easily flow? Which of the compound easily flow?
Water.
Water.
Water. Just because the water molecule is easily moving and ketchup is not easily moving, it means the interaction between the ketchup molecule is more as compared to the water molecule. So you can remember like this. Okay, so you'll have this particular topic in detail also in physics, but I'm just gave you the example. So should I start new topic now, or should I ask one question first? Okay, I'll ask one question. Just tell me which one of the molecule will undergo hydrogen bonding. Okay. Okay, 1, 2, 3, 4, 5. I give you the 5 molecules. Okay. So, which one of the following will not undergo hydrogen bonding? Okay, just tell me, water will go or not? See, there must be a proper interaction between you and me just for this particular case. If you'll not speak, you'll not learn. Just try. What will happen? Either it will be wrong, either it will be right. Okay, just speak it up. So,
Sir, it will go.
It will
it
go, sir.
will, yeah, it will go. What about HF?
Yes.
It will
Yes,
go.
sir.
What
It
about
will.
the ethanol?
No,
Yes,
sir.
sir.
Okay, what about this acetone?
It will be, sir.
It will be. And what about CH3CONH2? Amide?
Yes, sir.
It will be, sir.
See, everyone will go under hydrogen bonding because I
Yes,
told you
sir.
one thing, that if FON is present, then hydrogen bonding is present.
So in third one, we think OH, na, sir.
This one, CH3CH2OH,
Yes, sir.
it will also go under. It will also go under. This is ethanol. Ethanol will undergo C. I'll show you how. This is CH3CH2OH. This is ethanol. Take another molecule, CH3CH2OH. The interaction of this hydrogen and this oxygen will be there. So there is hydrogen bonding. Okay. Now, where there is a possibility where you can go confused. In case of acetone, in case of this acetone, there is a sort of thing where you'll not have hydrogen bonding possible. but it can go hydrogen bonding to a very little extent. Okay, so you'll see when you'll learn organic, you will learn why I'm saying this. Right now, you'll not understand, but very less extent of hydrogen bonding is present in this, just because of the hydrophobic character. You'll see. Rest example, they can easily undergo hydrogen bonding. Okay, next topic will be MOT, that is molecular orbital theory. See, molecular orbital theory, why we are learning it? Just because, see, one thing is there that just because old theory fail, we learn new theory. So the last main theory was VBT. So there must be some demerit of VBT. According to VBT, what will happen that one orbital and another orbital, they must have opposite spin. See, this is one atomic orbital, this is one atomic orbital. They will combine and they will form a new hybrid atomic orbital, molecular orbital. Okay, you can say they will form two new molecular orbital. Okay, so what was the first demerit of VBT is that VBT not talked about any, do not explain anything about the molecular orbital. VBT was not explaining anything about the molecular orbital. This is molecular orbital, and this was atomic orbital. So VBT was not able to explain about the molecular orbital. So this was the first drawback of VBT. See, what is the need of molecular orbital theory? That there was a drawback in the VBT. First thing. So just to clear about that drawback, we have to go for new theory, that was molecular orbital theory. So first demerit is that when S1s orbital, that is atomic orbital, they were combining, they were overlapping with each other, form the new molecular orbital. But VBT was not explaining the molecular orbital. Second thing, VBT failed to explain about the stability of hydrogen. Stability of hydrogen molecule. See, this is quite basic thing. If it was not explaining the molecular orbital, so hydrogen have 1s, another hydrogen has 1s. So they will overlap, they will form sort of this type. One with the positive spin, one with the negative spin. So this is molecular orbital. And H2 molecules, so there was no molecular orbital theory at that particular time, and that VBT was not explaining about the molecular orbitals. So interaction of 1s orbital of hydrogen to forming the one molecular orbital of H2. So stability factor, where is that stability factor? This was again the drawback. This was again the drawback of valence bond theory. Third drawback was that what about magnetic nature? What about magnetic nature? See, magnetic nature is basically, we have to learn two types in the chemistry. We have more type in the physics, but just remember paramagnetic effect and diamagnetic effect. Anyone know about paramagnetic and diamagnetic effect? What is paramagnetic compound? What is diamagnetic compound?
No, sir.
No? Okay, listen. Paramagnetic compound only arises when unpaired electrons is present. And diamagnetic only arises when there are paired electrons. But what's that effect? First question is, what's that effect? They arises just because of that, but What exactly paramagnetic and diamagnetic represent? See, in case of paramagnetic, what exactly happened? There is a attraction of that unpaired electron towards magnetic field. But in case of diamagnetic, since the electrons are paired, see, this condition must be there. But in this, paired condition must be there. So if paired condition, it means they get repelled by the magnetic field. So those compounds which get attracted towards the magnetic field just because of the presence of unpaired electron. But I said the compound which get attracted by the magnetic field just because of the presence of unpaired electron, they are called paramagnetic compound. While the compound which have all paired electron and are not getting attracted and get repelled by the magnetic field, that are called diamagnetic compound. Now clear? Paramagnetic, diamagnetic.
Yes, sir.
Okay, so if they get attracted, repel, so it means sort of some magnetic nature is there. So VBT again, there was no explanation by the VBT regarding the magnetic and magnetic nature, that is paramagnetic and diamagnetic. So these were the three main drawback of the VBT. So in molecular orbital theory, we came to know about certain factors such like bond order, bond length, diamagnetic nature, and stability of the compound. And last one is paramagnetic nature. So VBT tell you about these things: bond order, bond length, diamagnetics, and paramagnetic, and stability of the compound. So the need, just because there was a drawback in this, so we need to learn about the MOT, that is molecular orbital theory. And who gave the molecular orbital theory? F1 and R.S. Millikan. These were the two scientists who gave this theory, and improvisation. So that is necessary. So later on, whosoever do something new in this particular theory, we don't care about that, but we care about who invented this particular theory, that is F1 and R.S. Millikan. Okay. So now let's discuss about the postulates. Till now, if you have any doubt, then ask me. Rest, I'll start about the and this theory postulate. See, I think bond order you know, diamagnetic you know, paramagnetic you know, stability you know. Do you know bond order?
Yes, sir.
What is bond order?
Number of bond minus number of
See, that is the based on the molecular orbital theory. That is number of bonding electron minus number of anti-bonding electron divided by the two. But what exactly
yes,
the
sir.
bond? What exactly the bond order means? That is number of bond between the two atoms. Number of the bond between the two species. How many bonds are there? So for that, we need to calculate the bond order. Okay. So let's discuss about the postulates. I think I need to open new note. Okay. So let's discuss about the MOT. First thing what MOT told that atomic orbital combine to form new orbital called molecular orbital. It means one hydrogen atom, another hydrogen atom, they will combine and form molecular orbital. So two type of molecular orbital will form. So first point is atomic orbital combine to form the new set of orbital known as molecular orbital. Okay. According to MOT, they lose their identity. Atomic orbital lose their identity when they form molecular orbital. This was the first point. Second point was number of atomic orbital must be equals to number of molecular orbital. Say if two atomic orbital is there, then the formation of two molecular orbital will be there. One orbital is considered as bonding molecular orbital. Second thing is anti-bonding molecular orbital. So two type of orbitals is bonding molecular orbital and anti-bonding molecular orbital. Just give me 1 minute. So number of atomic orbital must be equals to number of anti-bonding number of atomic orbital is equals to number of molecular orbital formed in this particular case. So one is considered as bonding molecular orbitals and another one is considered as anti-bonding molecular orbital. Third point is only those atomic orbital form molecular orbital whose have comparable energy. You can say which have comparable energy. For example, 1s plus 1s, they can easily form two molecular orbital because they have approximately same energy. But if I talk about 2s and 1s, now there is no molecular orbital because there is a energy gap. More energy gap is present. So if same amount of energy or very small change in the energy is there, then there is a possibility of forming the molecular orbital. But if there is a large gap between the energies of the orbital, then there is no formation of molecular orbital just because of the large energy gap. Okay. Fourth point, what it tells that when two atomic orbital overlap, when two atomic orbital overlap, two molecular orbital will form. I explained this particular point earlier also, that two type of orbital, molecular orbital and anti-bonding molecular orbital. Okay. Fifth point is bonding molecular orbital has lower energy than anti-bonding molecular orbital. So what exactly happened? The bonding molecular orbital have always a lower energy than the anti-bonding molecular orbital. And you know, if anyone is having the less energy, the stability will be yes. If energy is low, stability will be more or high. Oh, more or less. Energy is inversely proportional to stability. Revise the past lectures. Energy is inversely proportional to the stability. It means if the energy is less, stability will be more. Sixth point, axial overlapping. Axial overlapping, which type of bond? Sigma or pi?
Sigma, sir. Sigma, sir.
And parallel overlapping?
Pi
Pi
bond.
bond.
Very good. So axial overlapping leads to the formation of sigma bond, and parallel overlapping leads to the formation of pi bond. And the last point is that bonding molecular orbital are denoted by sigma and pi, while anti-bonding molecular orbital represent as sigma star and pi star. This much is clear. I think points are easy. See again, just quick revision. Atomic orbital will combine to form new set of orbital known as molecular orbital. Second point, number of atomic orbital will be equals to the number of molecular orbital formed. Third condition, only those atomic orbital will form molecular orbital which have comparable energies. It means the energy difference is not that much. Next, when two atomic orbital were overlapping, two type of bond orbital will form. That is bonding molecular orbital, anti-bonding molecular orbital. Next, bonding or molecular orbital must bonding molecular orbital have low energy as compared to the anti-bonding molecular orbital. It means the stability of the bonding molecular orbital will be more as compared to the anti-bonding. Next, if there is an axial overlapping of the orbital, it means sigma bond will form. If there is a parallel overlapping of the molecule, it means pi bond will form. Seventh point, that is bonding molecular orbital is represented by the sigma and pi. If there is axial, then sigma. If there is a parallel, it means pi. But if I talk about anti-bonding molecular orbital, it means sigma star and pi star. You need to add the pi star on any of the anti-bonding molecular orbital. So these were the point of molecular orbital theory. Now we will discuss about the LCAO method of formation of molecular orbital. So this much is clear.
Yes, sir.
Okay. So okay. According to LCAO, that is linear combination of atomic orbital. According to linear combination of atomic orbital, the atomic orbit, there's a combination there's a combination of the atomic orbital. See, it is mentioned in the name LCAO, linear combination of atomic orbital. So there is addition or subtraction. There is addition of subtraction, okay, of wave function of atomic orbital. See, first listen this carefully, then you can ask the question. Okay. So wave function here is represented by sine. So two conditions can be there. Sine MO, yani molecular orbital, is equals to sine A plus sine B. Second condition must be sine MO is equals to sine A minus sine B. See, if you remember the Schrodinger wave equation, of second chapter, then when there was a wave formation, okay, just tell me what we call this upper one. Do you know the name? And just general basic thing. What is this? Crest.
Crushed.
And
Yes.
what is this?
Trough.
Trough or trough. Some say trough, some say trough. Okay. So what is if I'm talking about this, the distance of the wave above or below the line of propagation, then what is this known as? This is called
Amplitude.
amplitude. And according to the Schrodinger wave equation, it is considered as wave function and represented by sign. Okay, so two things are there. If I talk about the wave, if I talk about wave, then two things are there. See, remember this very carefully. This is psi A, atomic orbital of 1. And I'm considering this in form of one wave. So the wave is like this. Okay. And this is psi B. Now, if there is an addition of psi A and psi B, it means that what will happen? The crest of this particular wave, psi A wave, and the crest of psi B, they will interact. And what will happen just because of this interaction? There is an increase in the amplitude of the wave. So if the condition is there's an interaction of psi A and psi B and they add, they will form psi MO. So they will lead to the formation of bonding molecular orbital. If there is an addition of psi A and psi B, it means there is an addition of amplitude of two of the wave of psi A and psi B. It means the amplitude of the main thing will rise up. So see, you can see the difference. See the difference. Here amplitude and here the amplitude. The amplitude rises is because there was the addition of two orbital. So this is known as constructive interference. This is termed as constructive interference. Second condition is taking one atomic orbital psi A, and now the wave is like this. This is psi B. Now, see, just to remember, I told you psi A minus psi B is equals to psi star ABO, AMO. It means in this particular condition, the wavelength or the amplitude of the two of the radiation will lower down. The wave function will lower down, or there's a possibility of having a, see, if the magnitude of this and the magnitude of this is exact same, the line will be straight. There will be this is called destruction. So this is also known as destructive interference. Or if the magnitude is not equal, maybe the A is more or maybe the B is more. So there's this thing you can say the amplitude of the wave decreases. The amplitude of the wave decreases. So two type of interferences there. First one was constructive interference. Second was destructive interference. So in case of constructive interference, what was happening? Psi A was adding with the psi B. They were forming psi molecular orbital. While in case of destructive interference, psi A minus psi B is equals to psi star AMO. It means constructive interference will lead to the formation of molecular orbital, while destructive interference lead to the formation of anti-bonding molecular orbital. So two type of orbital formed according to the linear combination of atomic orbital, that is molecular orbital and antibonding molecular orbital. So for this thing, I'll show you one video. Wait, just look at this video. See, am I audible? Can you hear me?
Yes, sir.
Yeah.
Okay.
Yes, sir.
So if you see in above two cases, see the wave are going, amplitude is there, and when these two ray were combining, what will happen? See, two rays were combining, and when there's the formation of new wave, the amplitude is rising. You can see there's a rise in the amplitude between the two layers. See, the wavelength, frequency, phase, three things are showing there's a change in only the amplitude. And this type of interaction is called constructive interference. I found this video on the YouTube, and just to explain this, I'm taking the example. See, the amplitude will rise. So this type of interaction is called constructive interference. And constructive interference lead to the formation of bonding molecular orbital. Constructive interference lead to the formation of bonding. See, in this case, here, the two wave came having the same amplitude, and they combine, the amplitude will rise up. This is called constructive interference. That is called also superposition of the wave. But in case of destructive interference, what was happening? In case of destructive interference,
Straight line.
a straight line, or the amplitude will
Decrease.
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 See, in constructive interference, the maximum amplitude is there, while in the case of destructive, there is what will be there?
Minimum amplitude.
Either
Minimum am-
either minimum amplitude, or you can say there is a straight line. If the magnitude of the things will be, both way will be same, then it will a straight line. Otherwise, see, the amplitude decreases. Clear? So this is called the constructive and destructive interference. And remember, the constructive interference lead to the formation of this molecular orbital, and destructive interference lead to the formation of anti-bonding molecular orbital.
anti Antimolecular
So
orbital.
clear. So clear this much? Okay. Let's talk about sort of difference between the bonding and molecular orbital. Bonding molecular orbital and anti-bonding molecular orbital. Okay. So first difference is basic, that is one is forming the constructive interference while another is forming by the destructive interference. Okay. Next one is, first difference is psi is equals to psi A plus psi B. While in the case of see this, I'm writing anti-bonding here, bonding this side. Okay. So first difference, psi star is equals to psi A minus psi B. Second thing, they are formed by constructive interference. They are formed by destructive interference. Basic. Third, electron density in the region between two nuclei of bonded atom is more. It means when there is a two bonded atom, so there is a between the nuclei of the two bonded atom, the electron density is quite more. And here, just opposite, electron density will be less. Fourth, the basic difference, atomic orbital have lower energy they have higher energy. Okay, so four differences enough, I think. You can go for the four difference. Okay. Next one is, let's go with the configuration. Let's go with the configuration. Okay. For the energy level diagram, for the energy level diagram, see there is an increase in the energy. So for the energy level diagram, what we used to do, we use, see, basic example if you want to go, that we know that one is, see, you know above principle, in second chapter, above principle, in which we learn the configuration 1s2, 2s2, 2p6, 3s2, 3p6. Remember?
Yes.
Yes, sir.
So, and I think you all also have learned the quantum numbers.
Yes, sir.
Yes,
And
sir.
how many orbitals are present in the P?
3,
6.
sir.
Orbitals are three,
Yes.
yes.
Three, sir.
Electrons are six. Okay. So just, okay, I'm doing a configuration of what? Whoa. Fluorine. Okay. So I'm taking example of diatomic molecule, that is fluorine. Atomic number is 9. Just do a configuration. 1s2, 2s2, 2p. 2p have 3 orbitals. 2px,
5,
2py,
2py,
2pz.
2pz.
So 2px has 2 electron, 2py have 2 electron, 2pz have 1 electron.
1 electron.
Okay. So this is one atomic orbital. Okay, I'm taking one another. 1s2, 2s2, 2px2, 2py2, 2pz1. Is this clear? This is a basic thing. Okay. So, but since the atomic orbital of fluorine will overlap with the atomic orbital of fluorine, another fluorine, so they will form F2. Now we are talking about the molecular orbital. And when we are talking about the molecular orbital, it means we are talking about the MOT. Now, what will happen? See, I told you, when there is an interaction, so the number of atomic orbital combined must be equal to the number of molecular orbital formed. So this is one atomic orbital, this is one atomic orbital. They will combine, they will form one atomic orbital. One is, see, s orbital, which type of overlapping, sigma or pi?
Sigma, sir.
Sigma. So I'm putting
Sigma.
sigma in front of both right now. So 1s orbital of one fluorine will combine with the 1s orbital of another fluorine, and there is an interaction that is called that is called head on head overlapping. So that is called sigma bond. But see, two molecular orbital must be formed. One is starting one is considered as molecular orbital, another one is called anti-bonding. So I'm putting star over here. So one is sigma 1s and another molecular orbital is sigma star 1s. So two electrons, so two electrons. Okay. Next, again, the interaction of these two will lead to the formation of sigma 2s and sigma star 2s. Two electrons. Clear this much?
Yes, sir.
Okay.
Yes, sir.
The energy of px and py is approximately similar, but we know if pp orbital are combining, they are forming pi bond. So pi to px is equals to pi to py. Pi to px is equals to pi to py, and the last interaction is sigma to pz. See, I wrote the only bonding molecular orbital. Now I will write there anti-bonding molecular orbital. So anti-bonding molecular orbital will be pi star 2px, which will be equals to pi star 2py. Y, and another one is sigma star 2p Z. Now fill up the electrons. See, instead of this, just remember 9 and 9. 9 and 9, add on 18.
Yeah, 18.
So we have to fill the 18 electrons now. 2, 2, 2, 2. It means 8 electrons are filled, 10 more electrons. So see how we fill it. We fill it as 1 and 1. And then we'll go for pairing. So 2 electrons will also be there. So 2 here, 2 here, 2 here. How many electrons are filled? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Then 15, 16, 17, 18. Now, is the configuration is clear? So this is the electronic configuration of fluorine. So you just need to remember the interaction. See, I'll tell you one more type of configuration. But for diatomic molecule, like Li2, Be2, C2, N2, not O2, not O2, like this type of molecule, you will use this configuration. Okay, clear this much? Any doubt in this? Then ask, or else I'll go further. Okay, let's move. Another configuration is there's a simple, just a basic difference. Okay, just a basic difference that you have to, in some cases, the energy of pi 2px and pi 2py is lesser as compared, is more as compared to the sigma 2. See, this is the order also. The energy of sigma 1s is less than sigma star 1s. So this is the energy order also. In this way, energy is increasing. So in some cases, like the configuration changes as sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. This one is same. But the difference is sigma 2pz will come first, then pi 2px is equals to pi 2py. Then we will go for pi star 2px is equals to pi star 2py. Then sigma star 2pz. So just a simple difference is that they both get exchanged. For the molecule, like you can say, for the molecule like O2, F2, Ne2. O2, F2 or Ne2. Or you can go like that, the elements having the more than 14 electrons. Elements having more than 14 electrons, you will use this configuration. I'll go further in the next class just because we will need to make the energy level diagram also. And just go through this much at least in this particular chapter. And MOT especially. See, if you'll not revise MOT today, let me tell you one thing, you'll not understand anything in the next class. Just at least revise today's lecture just because this is important. Okay, so if you want to ask anything, you can ask me. The rest, I'll wind up the lecture right now, just because I know that this is quite much for today. We have learned a lot of things. We have started the molecular orbital theory. We have started the postulate. Then we went for the Lacau, that is linear combination of atomic orbital. Then constructive interference, destructive interference. For the first time, you have learned this thing. And then difference in the bonding and anti-bonding molecular orbital. Then energy level diagram, we have learned the configuration. So this is a quite huge thing. I know this will be quite more for you. But just at least go through it once. If you'll go through it once, it will take maximum 30-40 minutes. Just look in the 2x speed. It will go fast and it will be very easy to just remember. Okay, so first go through this class. If you want to ask anything, you can ask me in the next class. Let's wind up the lecture here, and you can join the next session. Enjoy your day. Thank you so much. Join another lecture, next lecture. The student leave this meeting and just join next class.